Hi, I'm Chris Brown, and this is lecture 2.14b on manufacturing processes in axiomatic design, in the course Axiomatic Design of Manufacturing Processes. So for the next few minutes, we're going to be talking about surface metrology and following up on the previous lecture. And this is a case study in correlation between die friction and relative area at a certain scale. So the objectives here are to go over area scale analysis, which goes beyond the traditional parameters that we spoke about previously. And the problem that we're addressing is trying to correlate roughness with performance. So roughness is a kind of design, roughness is a design parameter, and we're looking for ways to describe it that will correlate with performance and processing. And demonstrating the importance of scale. So the relative area is a scale-based analysis. So these multi-scale characterizations, these are possible DPs for specifying surface topographies. And these are essentially scale-based decompositions of the geometry of the surface. And so we looked at these previously, and so the one we're going to focus on right now for this work is area scale analysis and area scale complexity, which is its scale-based derivative. So area scale fractal analysis is something that we actually patented here at WPI some time ago. The patent has expired. It's now a national and international standard. It uses repeated virtual tilings in order to calculate the apparent area of a surface. Now, if the surface has got chaotic elements, the area changes with scale. And so then we make plots of relative area, which is the calculated area, normalized by the nominal area, versus scale. Now, the importance of area as a texture characterization parameter, so as a possible DP. So think of Newton's law of cooling. The greater the area you have, the greater the heat transfer, given a certain temperature differential and heat transfer coefficient. So area seems to be an important term here. It also comes up in mass transfer and flux. The greater the area you have, the more the flux is, the more mass you can transfer. Area should also be important in charge transfer for similar reasons. Load transfer and compliance, so the area of contact is going to be important. And discrete interaction models, and we've worked on adhesion, and it would also make sense for reactivity. The more area you have on a surface, the more reactive it should be, and the more sites you have for adhesion, for certain adhesion mechanisms. But the problem is that the area of the surface, as we've mentioned, is not unique. It depends on the scale of observation or calculation. So here's an example. This is a diamond coating that was measured a long time ago now with a nanoscope 2, one of the first scanning tunneling microscopes, and by my friends at the University of North Carolina, Charlotte. So we can see here that it's a collection of sort of little pyramids on big pyramids. Note the scale here is 10,000 nanometers or 10 micrometers by 10 micrometers. So these are quite small. We can see what looks to be measurement artifacts as the scanning was horizontal going back and forth. But there's a distinct pattern of sort of little pyramids on big pyramids. So what we do is we do this virtual tiling and multiple tiling exercises. The size of the triangular tile represents the scale. And these, for each tiling exercise, these are all close to the same. So as the scale in the tiling, the size of the triangle, is at this size, you get this many triangles, 18 patches on it, and the relative area is just above 1. Now 1 would be the minimum relative area. So if all of these tiles were lying flat, the relative area would be 1. And that would mean they were insensitive to the topographic details. All right, as the scale gets smaller, the number of patches certainly goes up, but so does the relative area. Even if the surface were smooth, we would expect the number of patches to go up because they're getting smaller, we fit more on. However, we don't, if it were smooth, they would go up by the same proportion and the relative area would stay about the same. In the case of a rough, chaotic kind of surface, the relative area goes up as the scale goes down, and that's what we're seeing here. So, so then we can do a plot, scale, log scale on the horizontal, and log of relative area on the vertical axis. And so at the very large scales, we can see the relative area is 1. Then there's a kind of smooth, rough crossover where the triangles start to fall into the valleys and climb over the mountains. And then we have a linear portion here where we see the scales over which it looks like a collection of little pyramids on big pyramids. And then we get down to a much finer scale where we're essentially putting the tiles on the crystal facets. So that's down here, starting around 4,000 or so square nanometers. So if we take a look here where this is starting, there's 1,000 square nanometers, so somewhere in 4,000 or so. This thing's leveling off, and the tiles are just seeing very smooth facets. So the steeper this negative slope, the greater the complexity. And so as we get down to the facets, there's markedly less complexity than there is at the slightly larger scales. And at the largest scales, of course, the surfaces appear smooth. So here's the experiment where we're going to use that. So we're looking at milled die steel surface roughness, and this would be a DP in designing the surface die, and correlating it with the sheet steel friction. So this is something you're trying to control inside a die. You've got sheet metal inside a die that's squishing it to make a car fender or something. And you want to be able to control the flow in there so that you get good uniform thickness, and you don't get these special orange peel effects, which would be unacceptable. So this was a collaboration. Johan Berglund was working on his doctorate, and at Sandvik at the time. And B.G. Rosen at Halmstad was one of his advisors, and he worked also with Neil By, so in Denmark. So we have the Scandinavian contingent, and then we were doing the calculations here, and Johan visited us. And this was published in the CIRP in 2010. So the idea is to try to find correlations between friction in sheet metal and the texture of the milled die. And so the idea is, let's see which characterization parameters work the best so we can tell which ones we might use for a DP, for example. So the tool texture controls the friction, and these are both FRs in the tool, or a DP and an FR in the tool design. And then the friction controls the flow in the forming dies, which might be a PV, for forming. So, so what are going to be the useful characterization parameters? And the usefulness here depends on the ability to find correlations. That's where the value is. So the method was to manufacture pins to create 6 different sort of kinds of surface roughness, measure the surface texture of the pin, characterize the measured texture with all these different parameters, and then test to see what the friction is, and then do regression analysis so we can test for how strong the correlations are. So here is the milling of this. So we're milling a cylindrical form with a ball-end mill, and there's 3 different materials that are being used, and here's the designations for those materials, and here's a brief description of them. And then there's 2 kinds of milling, so rough and fine. And these materials are different enough so that the rough and fine milling give us, together with the different materials, give us 6 distinctly different surface textures. And so here they are displayed without any filtering. And so just looking at this, we can say, yeah, they all look different. And in fact, we can tell the difference when we measure them. So here with the form removed, we can see 5 and 6 compared. So the coarser milling and the finer milling. So here is the SQ, or the root mean squared roughness of these 2. And then here is their friction coefficient. And the friction is tested in this tester at the Danish Technical University. So here is the milled pin, and then the sheet strip is dragged across it with under force, so that it's pressed well against the pin, lightly lubricated. So here are the different friction coefficients for in all the different cases, and here is the standard deviation of the friction coefficient. So one of the things we see that's a bit unusual in tribology experiments is a very low coefficient of variation, which is the ratio between the standard deviation and the mean. This is the mean friction coefficient and the standard deviation. All right, so how do these correlations work out? Well, not very well for the standard height parameters. So an r squared of 1 would be perfect, and these are approaching 0 for the most part. The only two parameters that are worth mentioning in terms of strength of correlation are probably surface slope and the developed surface area. So these are all standards now. The DIS 25178 is passed, and that's a ISO standard by now. The segmentation parameters, they're new kinds of functional parameters, and we didn't spend any time trying to adjust the different adjustable features on those, but that's how they came out. So here are the two best, the developed surface area and the slope, and with their regression equations and regression coefficients. So coefficient of friction and the parameter value. So now these are something that you could use in the design of the dies. So this would be, and these relationships between the friction and the roughness would be your design, part of your design equation. So one of the things we note is the developed surface area is very close to the relative area, and we sort of expect that because they're both based on triangular tilings, although the routine is slightly different for both of them. So therefore, the slope is not 1 and the intercept isn't 1, but the r squared is very high. Also, the gradient, you can't increase the area of a surface without increasing the slopes. So we expect that there's a strong correlation between the developed surface area and the gradient, and there is. So these are not essentially independent parameters. So when we have strong correlations on both of those, we don't really have any extra information. We're dealing essentially with the same information. So here's the relative area versus scale. And then the complexity was calculated as the slope of this curve and over a 1-decade interval, and it's done in a sliding manner so that we can have the complexity over the full range of scales. And here you can see sorted by color are the different pins, and they're so now we do the regression coefficient, and we do this at each scale. We do the regression. And so here there's not very much difference. So even if we get strong regression coefficients out at at the large scales, the small difference isn't going to be very useful. But somewhere in here, around 100 square micrometers, we start to see better differentiation between these, and it becomes more meaningful. So as we can see too, as we just get to 100, this is where the r squared starts increasing in a steady kind of meaningful fashion. And at about 7 square micrometers, the r squared is about 0.9. I didn't draw that line very well, but you can see there that, and there's a nice, smooth, steady trend in the r squared increasing as the scale decreases. So this tells us that something special is going on physically around 7 square micrometers that is controlling the friction in this case. And so it appears that the more the greater the relative area, the greater the friction at that particular scale. Now, if we go to the complexity, it's interesting there that we get an even higher correlation coefficient and at a different scale. So we're 200 micrometers, where there was the differences were just starting to show up in the relative area plots. So we can find an even higher correlation coefficient with the complexity, or area scale complexity, as it's called in the standard. Now, there's a second publication that was published in Scanning in that same year and presented at the International Conference on Surface Metrology, which we hosted here at WPI. And Johan was here and presented that, and he worked with Chikanamsu Agawamba, one of our master's students in mathematics here at WPI, and also with Brendan Powers, another graduate student, myself, and B.G. Rosen. So in this case, we're using a band pass method for filtering the measured surfaces. So using a high and a low pass, you can define different bandwidths depending upon how far apart they are in the frequency or wavelength space. So these are spatial wavelengths that we're describing, and it would be the inverse of the spatial frequency. And so we use different bandpass filters stepping along in the spatial wavelength space, inverse frequency space. And then we calculate the roughness parameters for all these different filters and then do the linear regression. So there's a lot of calculations, but it's very interesting what comes up. By the way, for the fractal, the area scale filtering or area scale analysis that we did and we just saw, there was no filtering, and we did more scales, and then the linear regression, as you saw. Now, the amazing thing in this is that whereas with standard conventional filtering, SA had a very, very poor correlation coefficient. It was down to 0.1 or something. When you use the bandpass filter, the correlation coefficient is very poor at the large scales, but then as we start getting down into these scales, now remember about 100 square micrometers is where we started seeing some differences. So this is so these are linear instead of square. So it's down maybe in this region here at the 10 micrometer wavelengths or so that we're starting to see the correlations or the differentiation in correlations in the other data. Here we are. We're seeing very high correlation coefficients with the average surface area. Basically, with all the bandwidths, we're getting up to about 0.94, which is even better than we were doing with relative area. And this is the average roughness. So this points to the importance of the scale. So if we filter and just have the right slice in the wavelength or frequency domain and try our analysis, then it works very well. So what we've done essentially, in some ways, is turned what we might have done is to turn average roughness into a kind of slope parameter by taking such a narrow chunk in the spatial frequency domain or the wavelength domain. So here's the regression line, and then this could be used, as I said, in design when we're trying to get a correlation between a design parameter and an FR. Now, it's not just average roughness, but we notice that all of these, the SDR does better with the filtering, the proper filtering, SQ. So all of these are above 0.9, SDQ, SMC. So these different parameters that behave so poorly with conventional filtering, with the right kind of filtering, can be very good predictors of the friction coefficient. So strong correlations for FRDP type can be found using appropriate filters. Several techniques might be used to find suitable cutoffs. So we were using bandpass filter. The scale-sensitive fractal analysis might be good, the area scale, for example. And I throw in wavelets here, although I've got no experience with them. The work that I've seen indicates that used properly, they might be able to come up with the same results. All right, well, let's take a broader view and see what sort of principles might be involved here. So when the surface is created or manufactured, there is a creation or manufacturing scale that's imparted into the surface texture. and this might be related to, say, the feed per turn in a lathe operation, something about the abrasive and the interaction with the abrasive in a grinding operation. So there are different scales that are going to be imparted on the surface texture depending on the process. Now, there's another scale for the behavior, the performance. So this would be like the friction in this case. What is the right scale in order to evaluate the performance? And here might be, what are the scales in the milling operation or in the microstructure of the material? So then the surface was measured, and we have a measured texture, and we talked about those having sometimes a million elevations. And that's far too many to work with by themselves, so we do some analysis. Now, as we've seen, there are some analyses that work better than others. So what's the difference here? So we're getting some sort of texture characterization, and we have some way of characterizing the surface manufacture, like the feed and the microstructure, which we haven't developed much in this case, or the behavior characterization, which was sort of our main point. And in that case, it's the friction. And so what we're looking for is ways of finding, in this case, was functional correlations between the texture characterization and the behavior. And so in order to find these, we need to preserve the right scales at which this interaction is taking place from the measured, from in the texture, first of all. We have to have measured them, and then we have to analyze them appropriately. And that sort of ties back to what do we need to find these kinds of interactions. We need good measurements, the right scale, and the right geometric feature. So what are the trends in manufactured surfaces? And we'll be taking a look at more details on these later. But it is better control of the surface formation and trying to push smooth form and smooth features to finer scales. Another thing we'd like is better and faster measuring, and people are now trying to do this more in the machine tool, so corrections can be made in the machine tool. And as we've seen, we're doing more sophisticated analyses. So this needs a better understanding of fundamental processes. And excuse me just a moment. And of the tool workpiece interactions. We need to understand the surface interactions for understanding the performance. So just some quick acknowledgments. We've gotten support in the surface metrology lab where this work was done. Generous support from Olympus, who's given us a confocal microscope to use. Digital Surf gives us software. Safina Machine Tools has supported our research for a few years. Solarius has also supported us with equipment, and Mezzo has supported our research. And SFRAX, which is the software for the scale-sensitive fractal analysis, the area scale analysis, is owned by me. So if I seem to be enthusiastic about that, that might be one reason. Thank you for your attention.